Folks, this is a black hole. And today in this lecture, I'm going to show you how to calculate the energy of a particle orbiting a black hole. So let's say we have a small object. This could be a planet, a star that's about to get sucked up by the black hole. Any particle orbiting the black hole, I'd like to calculate its energy and its angular momentum. So that's what we're going to do in today's lecture. I'm your host, Ref Bari, Brown University physics grad student. Let's get started. So, how do we calculate the energy of a particle orbiting a black hole? To answer that question, as with any question dealing with a black hole, we have to start with the Schwarzschild metric. The Schwarzschild metric tells us essentially how time and space wrap, how they change, how they twist and turn around a black hole. The Schwarzschild metric applies for black holes that are not rotating or black holes that don't have any charge. So let's go ahead and write down the Schwarzschild metric. So the Schwarzschild metric is made out of 4 pieces. Why does it have 4 pieces? Because, as you might remember, space and time are 4 dimensions, according to Einstein. So to describe any event in space and time, I need 4 coordinates. I need a time coordinate, t, and I need 3 space coordinates, x, y, z. So just to give you an example, let's say you're meeting up a friend for dinner. Now, in order for you to meet up with your friend needs to tell you when to meet them, but also where to meet them. So for example, let's draw a space-time coordinate system. Here I have x, and here I have t. So let's say I'm standing here. The whirl line of a standing stationary observer is just a straight line on the vertical axis. Why is it just a straight line? Because I'm not moving in the x direction. I'm just moving through time, right? Let's do that again so that you understand what I'm doing. So imagine that I just have a person standing still. What would their graph look like on the x-t axis? Well, if a person is standing still, they're not moving in the x direction, but they will be moving in the temporal direction, right? No matter what you do, even if you're standing still, you'll still be aging. You'll still be moving 1 second forward in time every second. So that means your whirl line will evolve like this. You'll be moving in time even if you don't move in space. So let's say that this is Ref's whirl line. This is Ref's whirl line. Whirl line is just a name for how you move through space and time. So if I'm just standing still, this is how my whirl line looks like. I'm just moving through time. Now, let's say I have to meet up Bob for dinner. Now, Bob tells me that dinner happens at a specific location at a specific time. So let's say dinner happens at Chipotle, which is at some given location, x naught, and at some given time, t naught. Okay, so this is where dinner is going to happen with Bob. So to specify when the dinner happens, Bob needs to give me the time coordinate of the dinner. And to specify where the dinner happens, he needs to give me the x, y, and z coordinates of the dinner. Okay? And this is basic special relativity. To specify where and when any event happens, I need 4 coordinates, 1 time coordinate and 3 space coordinates. Yikes, there's a hair in my eyeballs. Anyway, so that's not part of the lecture. So this is all sounding good, but what if there's a black hole near Chipotle? Well, this black hole near Chipotle is going to warp. It's going to twist our sense of space and time. The black hole is going to affect how clocks tick near Chipotle and how rulers measure length near the diner. Okay? So somehow we have to account for the fact that there's a black hole changing these 4 coordinates, t, x, y, and z, near the diner. Okay? So how do we do that? We account for those changes in our 4 coordinates by using the metric. The metric tells us how each one of these coordinates change. Now, let's erase all of these. Now, what does a metric really tell you? Here's what a metric really tells you. A metric is just a small step in space and time. What do I mean by that? Here's what I mean. Imagine I have a blank sheet of paper and I give you 2 points on the sheet of paper. So here are 2 points, A and B, on the sheet of paper. Now, if I give you the x and y coordinates of these 2 points, you should be able to tell me how far away these points are from each other. How? Well, you just take delta x, how much separated they are in the x direction, and delta y, how separated they are in the y direction, and you write down the Pythagorean equation, the Pythagorean formula. Delta x squared plus delta y squared is equal to delta s squared. Well, delta s is the length of this line. If you're more familiar with it in the other form, a squared plus b squared is equal to c squared. This is just the Pythagorean formula, right? It tells you how long this hypotenuse is in terms of the legs of the triangle. Einstein actually proved the Pythagorean equation when he was only 12 years old. Now, this Pythagorean formula might look simple, but it has profound consequences when we move to special relativity. In special relativity, the Pythagorean formula gets upgraded, and it gets upgraded in this way. Einstein says that not only, first of all, Einstein says that we need 4 coordinates to describe any event in space and time, right? We need time, and we need 3 space coordinates. So that means we can't just settle for x and y. We also need to add z, right? We need to add the z coordinate here. So that upgrades this to 3 dimensions. But that's not enough, because to describe any event in space and time, we need to know not only where an event is happening, but also when the event is happening. So we need to add time to the Pythagorean formula somehow. So time is a very different dimension than space. And so it turns out that time comes with a minus sign in the Pythagorean formula. So we have minus delta t plus delta x plus delta y plus delta z squared is delta s squared. So this is how the Pythagorean formula looks like in special relativity. But we need to modify it one step further if we need to describe a black hole. Actually, before we even get to a black hole, let's see, is there anything else I'd like to say here? So this is good. This is the Pythagorean formula for 4D flat space and time. What do I mean by flat space and time? I mean the following. This is called a metric. Okay, this right here, this equation is called a metric. We no longer call it the Pythagorean formula. We could, but in general relativity and special relativity, Einstein calls this the metric, because it gives you a sense of how time and how space change in either a flat or a curved background. So this is the metric for a flat 4D space-time. Okay, so this metric describes flat 4D space-time. It tells you how clocks tick on flat 4D space, and it tells you how rulers measure length in flat 4D space. Why is it flat? Because there's no black hole here. There's no stars or planets in this background geometry. If there were, we'd have to use the Schwarzschild metric, which I'll show shortly. And why is this a 4D metric? Because there's 4 coordinates. There's a time coordinate, when is the event happening, and 3 space coordinates, where is the event happening. Now, if we'd like to describe something like a black hole, then we need to go to something called spherical coordinates. Spherical coordinates describe a sphere, okay, as the name implies. So to use spherical coordinates, we'll actually have to change from x, y, z to a different coordinate system. So here's what I mean. For flat, for something like a plane, for something like just a plane like this, I can use x, y, z coordinates, just flat coordinates. But to describe a sphere, I'm going to need to use something called r, theta, phi coordinates. And I'm going to explain what that means. What is r, theta, phi? So r is what radius are you on the sphere? So here is r. Let's say I have a point on the sphere. Maybe I'll put the point a little bit more higher up. So here's a point on my sphere. This point is some radius away from the center of the sphere, okay? But this point also has some angular coordinates, okay? What are the angular coordinates of this point? Well, first of all, if I draw a straight line vertically through the sphere center, then this angle, let's erase the r from here. This angle between the straight line, the straight vertical line, and my vector to my point, this angle is theta. Okay? The line, the distance from the center to my point is the r coordinate. And finally, the angle that, if I draw a line down from my point to the plane, and I make this line, then this angle here is the phi coordinate. So that's what r, theta, and phi are. They're just ways to measure different points on a sphere. These are the three coordinates you need to tell you where you are on a sphere. So, and these are the three coordinates you need, x, y, z, to describe where you are on a flat 3D spacetime. So if I have, for example, x, y, and z here, then to describe any given point, I need to tell you where the x coordinate, okay, there's clearly no y coordinate for this. Maybe I'll put the point here. So if I have a point in just flat space and time, I'll need to tell you what the x coordinate, what the y coordinate, and what the z coordinate of this point is. Similarly, if I have a point on a sphere, I need to tell you what the r coordinate, what the theta coordinate, and what the phi coordinate is. Remember, the theta coordinate is this 3D angle. This phi coordinate is this planar angle, this planar angular displacement from the x-axis. Okay, so if I now rewrite this metric for flat space and time using spherical coordinates instead of x, y, z, then here's how it looks like. So my metric is going to change as follows. So I'm going to still have my minus delta t squared. Okay, this delta x squared is now going to be replaced. Instead of x, I'm going to use r. It's going to be replaced by delta r squared. Instead of delta y squared, this is going to be replaced by delta theta squared. And instead of delta z squared, this is going to be replaced by delta phi squared. And this is all going to equal delta s squared. Now this is very close to the correct answer, but not quite. See, there's a small correction I have to add here. Here, I have to add an r squared, and here, I need to add an r squared sine squared theta. Now this would be the correct metric for spherical coordinates. Why did I need to add an r squared and r squared sine squared theta? Where did these come from? Well, one way you can see that is as follows. If I have just a circle, imagine I just have a circle. Let's just draw a circle right here. And let's say this circle has some radius r. And let's say that I carve out a kind of pie. And this pie shape, this little slice of pie has an angular size of theta. How big is this arc length here? Well, we can find that out. We can find out the size of this arc length pretty simply. The size of this arc length is however big my angle is out of 2 pi times the circumference of my circle. If I multiply these two things, I get r theta. So that's the size, that's a tiny arc length of this pi. Now, if I just replace this theta with a d theta, okay, that means this tiny length, dl, is simply r d theta. Now, notice here that my metric is squared. My length is squared. So now if I square both sides, I get that dl squared is equal to r squared d theta squared. So now notice that's exactly what I have here. If I just replace d theta by delta theta, they mean the same thing, then r squared delta theta squared is exactly what I have for this theta term of my metric here. This delta phi term, r squared sine squared theta delta phi squared, comes from a very similar idea. So here's where that comes from. To illustrate where this comes from, I need to upgrade to 3 dimensions. So let's erase all of this. So imagine I have 3 dimensions. Here's my z-axis. Here's my y-axis. Here's my x-axis. Imagine I have some kind of a circular wedge. So here's my, this is going to be either very good or very bad, depending on how it goes. Okay, good. So let's try to make it look 3D. So I'm going to have a circular wedge, and I'll connect it to the origin of my coordinate system. Okay, there we go. So here is my little circular wedge. Now, I'd like to know how much the total length, if I take a small step in the phi direction, how much will the total length increase? So what do I mean by that? Here's what I mean. Maybe I should draw this differently, but anyway. Let's take one of these points and project it down to the xy plane. Okay? And let's take another one of the points and project this down to the xy plane as well. So this angle here, this angle on the xy plane is d phi. Okay, it's a small step in the phi direction. Remember, the angle on the plane was the phi angle. The 3D angle, this 3D angle was the theta angle. And this angle inside of my circular wedge is d theta. It's a small step in that theta direction. So anyway, the question is this. If I take a small step in the phi direction, in the d phi direction, what is the actual change in the length of my circle, right? So if I take a small step, imagine you're an ant and walking a small tiny step along this phi direction, what is the change in the actual length of this circular wedge? Okay, depending on how much you step on the phi direction. That's the question we're asking. And here's how to answer that question. So if I call this length, if I call this distance of the point from the origin, let's call that r, okay? Now, if this angle is, let's say for the time being, that this angle is theta. Okay, I'm just going to erase this. Just for simplicity, let's say that this angle is theta. Well, if this angle here is theta, then this angle here also has to be theta. So again, I'm saying that this angle is theta. That means this angle also has to be theta. But if this is r and this is theta, then this here is r sine theta. Okay? And so if this is r sine theta and this is d phi, then remember from our previous equation, remember that when we did something like this, where we had a circle of radius r and a small step of length theta, that this arc length here was r theta. Just multiply them. So similarly, here if we have a step of r sine theta, a radius of r sine theta, and an angular step of d phi, this angular step, this arc length here is simply the product of them. So this right here is simply r sine theta d phi. So there you go. That's the answer. That means a small step in the phi direction is simply r sine theta d phi. And so now, if I just square both sides, this is r squared sine squared theta d phi squared. Why did I square both sides? Because the metric is indeed squared. And so that's why the phi term of my metric is r squared sine squared theta d phi squared. So that's where each term in this metric comes from. So we've now seen how the metric looks like in flat space. We've now seen how the metric looks like if we want to describe flat space. This is still flat space, but we're just describing it using spherical coordinates, okay? Now we are ready to see how the Schwarzschild metric, how the black hole comes in to all of this. So first of all, let me rewrite this with all of the bells and whistles of spherical coordinates. So I'm going to write what we just learned one more time. So we're going to have minus delta t squared. Again, we're just describing flat space, but we're using spherical coordinates to describe flat space. That's a bit of a tricky idea to get your head around, but that's the idea. So I replace delta x squared by delta r squared. Instead of y, I'm going to have theta. Remember, I'm going to have r squared, theta squared. And instead of z, I'm going to have phi, but remember, I'll also have this coefficient out front of r squared sine squared theta, delta phi squared. And now you know where all of these bells and whistles, these r squared sine squared thetas, and all of these things come from. Okay, so this is flat space using Cartesian coordinates. This is flat space using spherical coordinates. Now, let's describe curved space using spherical coordinates. In other words, this is going to be the black hole. So here's the black hole metric. The black hole metric is very similar to the spherical metric, but it's going to change how time ticks and how rulers measure length. So it's going to change only this t component and this r component. So let's see what all that's about. So I'm going to have minus 1 minus 2gm over c squared r whole squared delta t squared. Okay, actually this is not squared. So this is minus 1 minus 2gm over c squared r. I'm going to explain where all of these things come from. Plus 1 minus 2gm over c squared r to the negative 1 delta r squared plus r squared delta theta squared plus r squared sine squared theta delta phi squared. All of this is equal to delta s squared. Okay, this is the equation of a black hole. Okay, what does all of this mean? Hopefully you can see the end of this equation up here. Okay, first of all, notice that the angular terms of the black hole metric are exactly the same as the angular terms of the spherical metric, right? Nothing new there. What is new here are these terms in front of delta t and delta r. Where are these equations coming from? And the answer is, this is the event horizon of a black hole. So here's what I mean. Let's erase all of this. Let's draw a black hole. So here is a black hole. And the most important thing about a black hole is that once you cross the event horizon, once you cross this event horizon of the black hole, then no matter what you do, even if you're light, you have no choice but to fall in to the singularity of the black hole. So the event horizon of the black hole is located at a distance called r sub s. R sub s is the Schwarzschild radius of the black hole. It's called the Schwarzschild radius because Carl Schwarzschild is the first person who discovered the black hole metric. So it's named after him. So the radius of the black hole is simply the Schwarzschild radius. That tells you how big the black hole is. And we can calculate what the Schwarzschild radius is based on the mass of the black hole. Bigger black holes, heavier black holes are simply more massive. So the Schwarzschild radius will turn out to be 2gm over c squared. That's where this term is coming from. Now, where did I get 2gm over c squared from? Well, you can derive it in a simple way, but not really truthful way using Newtonian mechanics, or you can derive it using general relativity. Let's derive it using Newtonian mechanics for the time being. So the idea behind deriving the Schwarzschild radius is simple. The idea is that imagine you're a beam of light and you have just barely enough energy to escape the black hole. Maybe you're just outside the event horizon. Well, when you're on the very edge of the black hole, maybe you have a lot of kinetic energy. Here we're treating light as a particle, which you really shouldn't do. There's so many things wrong with this argument, but let's just use it to derive the Schwarzschild radius. Just for now, derive it hand wavily. So the idea is that you have some particle, maybe it's a photon, a beam of light, that has just enough kinetic energy to escape the black hole. Maybe it's just at the edge of the event horizon. So when the photon is at the edge of the event horizon, it has a lot of kinetic energy. By the time it has gone arbitrarily far away from the black hole, it has lost all its kinetic energy, but we know energy cannot be lost. So that means all its kinetic energy has now been converted into potential energy. So that means we can write that whatever kinetic energy the photon had in the beginning is now equal to its potential energy. Now we know the equation for kinetic energy is 1/2 mv squared. Now this is wrong in many ways. Number one, because light doesn't have a mass. I mean, this is just, imagine maybe you have a particle that has just enough energy to escape the black hole. Maybe I shouldn't have said light. And the potential energy is minus gmm over r. So m is the lowercase m is the mass of my particle that's escaping the black hole. Capital M is the mass of the black hole itself. Now, if I set the escape velocity of the black hole to the speed of light, then I can replace this v with c. And now I can cancel out the mass of the particle from both sides. And so now I have c squared over 2 is minus gm over r. Okay, so now I can just, I forgot this is just, I can just write gm over r. So now I can just solve for the radius of the black hole, solve for r. So I can bring c squared to the other side, bring 2 to the other side, and I don't know if I'll have enough space here, so let's move down here. So this tells us that the radius of the black hole is 2gm over c squared. So that's the radius of the black hole. And so that's where this term is coming in. This is 2gm over c squared, which, as you can see, is the Schwarzschild radius. Likewise, here we have 2gm over c squared, which is also the Schwarzschild radius. So really, if you wanted to, you could write these equations as follows. Minus 1 minus the Schwarzschild radius divided by r, how far away are you from the black hole? That's going to tell you how slowly time ticks on your watch, delta t squared, plus 1 minus rs divided by r to the negative 1. So this is the reciprocal of this expression. Here there's no reciprocal. That's going to turn out to be very important, times delta r squared, plus your angular terms, r squared delta theta squared plus r squared sine squared theta delta phi squared is equal to a tiny step in space-time around the black hole. So that is the full derivation of the Schwarzschild metric. I know that's not what I promised at the start of the video. I did say that I was going to derive the energy and angular momentum of a particle as it orbits the black hole. But this is the first step in getting there, okay? Because without the Schwarzschild metric, you cannot do anything. You cannot find the energy, you can't find the angular momentum of a particle around the black hole. This is where it all starts and ends. So let me just recap what we did. We started with something very simple, which was the Pythagorean equation, the Pythagorean formula. A squared plus b squared equals c squared. And then we said that Einstein requires 4 coordinates to describe the location of any event in space and time. You need to tell me where something is happening, so you need to give me x, y, z. You need to tell me when something is happening, so you need to give me time. So that's 4 coordinates, x, y, z, t. So we have to upgrade the Pythagorean formula so that we have t, x, y, and z. And so that's what the Minkowski metric is. This is called the Minkowski metric because we have time and we have 3 spatial coordinates. And when you add all of these up in a very similar way to the Pythagorean formula, then you get the length of a small step in space and time, delta s squared. Notice that time comes with a minus sign. So somehow time is very different from our 3 spatial coordinates. Now, if we want to describe flat space and time using not Cartesian coordinates x, y, z, but spherical coordinates r, theta, phi, then we need to upgrade to this spherical version of the Minkowski metric. So again, we have delta t, but instead of x, I have r. Instead of y, I have theta. Instead of z, I have phi. And I showed you what r, theta, and phi represent on a sphere. And then finally, to describe a black hole, since a black hole is a sphere and it has spherical symmetry, we need to use the spherical metric to describe a black hole. But we also need to account for the fact that a black hole warps the way that clocks tick and rulers measure length near the black hole. So that's why we need to add these kind of warps, space and time warping effects near the black hole. So that's what these terms are. And the angular terms remain unaffected by the black hole. So angles just are just as normal around the black hole, but space and time are heavily distorted as you approach the event horizon of the black hole. And so this was the final, more simplified version of the Schwarzschild metric, the black hole equation that we wrote down in the end. So in the next episode, we're going to actually do what I promised, which is use this equation to derive the conservation of energy for a particle around the black hole and derive the energy and angular momentum for a particle orbiting a black hole. So thank you for watching this episode of physics. I hope you enjoyed it. If you have any questions, leave them down in the comments below. I'll see you in the next one.